And good evening, everybody. Welcome to this part 2 deep dive as we explore GeoGebra's graphing calculator and geometry apps here within the next hour. I'm so excited to share with you what I'm about to share with you tonight. I'm excited and thank you for joining me. My name is Tim Brzezinski. I'm the Professional Development Director at GeoGebra. Prior to that, I was an independent math ed consultant for about 2.5 years or so. And even before that, I taught full-time high school mathematics at Berlin High School here in Connecticut, and also part-time at Central Connecticut State University. And throughout all my teaching career, one of the thing that I love the most, again, as I said before in other webinars, my philosophy of education has always been active, student-centered, discovery-based learning. That's it. The direct lecture was my last resort. I mean, I hated direct lecture when I was in high school and in middle school and whatever. And so, you know, students, we could tell students till the cows come home, they're never going to remember a lot of them. But we have a higher probability of remembering concepts that we are actually engaged with. And so I am a huge fan of many math ed tech apps. GeoGebra happens to be my favorite because, quite frankly, there's nothing that I have found that it cannot do to foster the discovery learning that I want to foster with my students. But again, you know, I use whatever I have available. But if I have GeoGebra, you know, I run to it because their suite of apps is just unbelievable. Their suite of apps are absolutely unbelievably powerful. And again, we're going to take a deep dive into the graphing calculator and geometry apps only tonight. But again, there's several apps. There's several webinars we've had in the series before. If you go to GeoGebra's YouTube channel, you'll find them right there, front and center, in the first swim lane there. But let's get started. We'll rock and roll. I'm going to share my screen, and yeah, let's do this. So right here, we are at GeoGebra's main page here. It's www.geogebra.org. Okay, we are here, and we're actually going to take a look at. Let me just minimize that for a second. There we go. We're going to actually take a look at the graphing calculator geometry app. So if you want to take a second and sign in, because you might make a construction tonight and want to save it, that's cool. Right up here where you see my mugshot, feel free to click the sign in icon and create an account if you don't have one. And if you do, take a second or two to sign in. Okay. Yeah. So as you're doing that, I just want to highlight something here really quickly on GeoGebra's main page, the main swim lane right here. We at GeoGebra, we've compiled a lot of great elementary, middle, and high school and resources available to you to use at any time, whether you're in the classroom and even right now during this unfortunate season of necessary distance learning. Okay, so feel free to explore any of those activities and resources. If you want some more information on how you can integrate them very well, painlessly into Google Classroom, OneNote, a lot of other LMSs, check out GeoGebra's YouTube page. There's how-tos there. But tonight, I don't want to waste time. I want to get going here. We're going to explore the graphing calculator and geometry apps, which are the top two options right here. Okay, we're going to actually explore the graphing calculator first. Okay, when you go there, you might, I don't see the notification myself, but if you go there for the first time, you'll notice that you get this big announcement that says, hey, you know, due to, we want to be compatible for many high stakes exams as much as possible. So GeoGebra has removed the geometric construction features from this calculator. Okay, you want to be able to construct a midpoint, or you want to be able to graph a circle or perpendicular bisector, find the slope of a line, you name it. All those tools are available within their geometry and classic apps. Okay, but for now, for the purposes of high stakes testing, within many state departments of education here in the United States, maybe other parts of the world, GeoGebra has removed that functionality from this app in order to accommodate that. And I could just say this really quickly. GeoGebra graphing calculator for any exam governing body, whether it's a Ministry of Education, whether it's a State Department of Ed, doesn't matter. If any exam governing body wants to integrate GeoGebra's graphing calculator within any testing API, it is absolutely free of charge as long as it's for the purposes of assessment. Okay, absolutely free. So let's take a look here at what we can do. Now, granted, many of you, we looked at this in part one. And yes, we have a limited tool selection here. Geometry app offers way more tools for that very reason. It has a lot more power. right? Think of this GeoGebra graphing calculator as the equivalent of a TI Inspire in full-blown exam mode with a lot of those features shut off so that they're compatible for many of those high-stakes exams that have those restrictions. So I just want to actually, yes, we'll learn how to use the apps, but more importantly, how can we pedagogically use this app to foster discovery learning within our classroom? All right. So to do that, I'm actually going to take, we're going to actually just plot a few points there. Point tools right here. Again, in the graphing calculator, you have your algebra view, which is the calculator symbol right here. You have your tools, which are the circle triangle right here. And over here, you have your table. Okay, any tables you make. So we're just going to go to the tools. We're just going to plot a point, right there. So I'm actually going to choose to plot points right on the x-axis. Again, you want to make sure that that finger kind of looks like, this in a way, that finger there. I'm just going to plot, let's say 5 points there. Okay. All right, 4 and 5. There we go, A, B, C, D, and E. And remember from last webinar here, whenever you see how the point tool is still turned on, we need to turn that off by selecting the move arrow down here. Now we can freely move these points around. Okay. Now, cool. I'm actually going to go up here to the settings gear, that you see right here. I'm going to hide the minor grid lines. So we'll go to settings. Where is it? Under grid. We can actually, under settings grid, I'm just going to choose maybe major for now. Kind of makes it look cleaner in my opinion. Not necessary, but you get what I'm saying. You can select and format many objects at once here, which I'm going to do. So under edit, right over here, you'll see the select objects feature. It's save work smart, not hard. If I lasso all these points by dragging a rectangular box around them like this, I can actually format all of these points at once. For students especially, I like to just make points very movable, if that makes sense. And maybe I'll actually turn the labels off. Oh, the values of the points are the coordinates, turn off the values, turn on the labels, whatever. You can do it any way your heart desires. If you are finding that you have 13 decimal digit accuracy, like numbers look crazy long, you can adjust that here as well. Under the settings, upper right corner, go to settings one more time, and it's under settings again right here, the third settings gear. You can actually check this out. This is pretty cool. You can actually round it to as many degree accuracy as you want. You chemistry teachers, if any of you are watching, you got your sig fig rounding there. You're welcome. Font size, if you're displaying to the class, you want to have a big font size there. Another thing I love about GeoGebra's apps, look at the language settings. I think there's over 72 languages from which you can choose. So if you have a student whose native language is not the language spoken in the particular country that you teach, you can easily have that accommodation right here within GeoGebra's apps. Every one of them. GeoGebra is all about community. GeoGebra has a team of volunteers literally all over the world that whenever something new comes out, maybe it's an app or a new website feature or whatever, they have a team of volunteer translators all over the world that are very excited to share what's going on, and it's awesome. And I am honored and I'm proud to be a part of that international community. It's really, really cool. So anyway, I digress. So here we have 5 points. So what I'd like to do now is, again, take a traditional lecture and what we often tell students and just kind of throw it back at them and have them tell us something that they notice. What do they see, right? So let's actually go in here and type in the word box plot. That's a common, upper elementary, lower middle school statistics, right? We have kids find the mean, the median, the mode, right? The interquartile range, all that jazz. Yes. Okay. But right here, box plot, let's just open parentheses here. Actually, no, wait, I apologize. I have to do something first. I actually have to make a list. So to do that, I need to make a list of data first in order to make a box plot from it, right? So let's actually, we need the funky brace symbol, like the nice little elegant looking brace. The one that you draw the left side perfectly, but the right side, it's like, all ugly, Am I the only one? I think you do that too, right? So I did a math class. So we have 5 points here, A, B, C, D, and E. So what I'm going to do is I want to make a data set containing only the x coordinates of these points. So to do that, I'm just going to use GeoGebra notation here. If I want the x coordinate of point A, for example, see how the x coordinate of point A is 3. I'm just going to type x of A, and notice that I see 3 right there. I want the x coordinate of B, x coordinate of C, x coordinate of D, and x coordinate of point E, say. Okay, and I'll hit enter there. So I have a data set now of 5 items. All right, and it's just filled right there. Granted, the data set will change. See how that first element's changing as I move this point here, right? So now what I want to do is I want to make a box plot from it. I can construct box plots really easily in this calculator with greatly reduced functionality. Again, geometric constructions features are removed, but again, anything that is needed for a high stakes exam is on this calculator. It is in this app, all right? And to make a box plot, I just simply use the box plot command, as you see right there. You see, GeoGebra Graphing Calculator has tools, right? There's a lot of tools shown here. The most popular tools are the ones that you see here. But behind every one of these tools is a command, okay? So, but GeoGebra has hundreds of commands built within their apps, but they only show a few tools because, you know, if GeoGebra actually showed like an icon for every single command, it would be an encyclopedia of over 600. It would just overwhelm you, right? So, but right here, and whatever I don't know, oftentimes I'll Google it and I'll find it right away. But I want to make a box plot from L1, and here's how I have to type it in. We'll talk about what the parameters mean in just a minute. I'm going to type in 2, and then a 1, and then the name of the plot, the name of the list, which is L1. Okay, I will explain the meaning of the 2 and the 1 in a second, but let's see what we have. Ooh, check it out. Okay. So let me see here. What if I made that first 2 a 3? By the way, feel free to type in the YouTube chat. I am watching it a little bit here. If I made that a 3, or if I make that, can anybody on YouTube tell me what that actually, what is that first parameter, 4 or 5 or 6? What's it actually doing? And by the way, I ask students the same questions too. You see, it's like, why should I tell students if they could play around with it and actually have them tell me, even the simplest of things, right? What is that first number here? How does it affect the box plot at all? 7, 8. I know with the 10-second delay, I want to respect the time, but again, notice here, that's really the midline of that box. See 7 here? I can make the midline -3. See how it brings it right down here? So I can actually make multiple box plots and stack them on top of each other. All right, if that makes sense. So regardless, let me bring it back to 2 here. And this 1 here, again, simply actually tells you, it actually is think of it as like the amplitude of the box, even though we're not talking trig here. But again, see how half the box height is 2? It's called the offset there. So I make it a 1, I can make it a 1/2. See what I mean? It'll make it smaller. You get what you guys say. And then the name of the list comes right after there. But I like to use these parameters here. But check it out. You see, I like to zoom in kind of like right over here and just have kids play with the data. Like, okay, guys, you know, what's going on here? As I do this, I can actually change the box plot as I do this. In fact, let me hide the grid altogether. I just want to not show it. Maybe this is better. I don't know. Right? But if you look here, right? Students actually can play with this for a few minutes and start making some observations. What can we as teachers ask our students about something as basic and simple as this? You know, I mean, students oftentimes they'll play with this for a couple minutes. They'll notice, wow, like the minimum value is always at this tail end, right? The max is always at the other tail end here. But you know what? It's like that middle line right there is always like, it's always over the middle dot. It's like I have 5 dots, right? And that middle data value there is always where that number 6 is right there. So, you know, and so then I'll say to kids, okay, well, I'll say, yeah, well, you know what, that maybe what you're saying is true. I like it, but what if we were to take that out altogether? What point is this right here? Let me show the label. Oh, that's point C, right? So I'll tell you what I'm going to do. I'm actually going to take C out of this list altogether. Again, we could change this list anytime we want to. See, I'll take X sub C out of it. I have a new box plot now, And now I can pretend that, see how C isn't doing anything? Let's just actually, let's actually trash it. Now, what do you think that middle line there is actually, what do you think that middle line is now? The kids are looking at it, huh, okay, you know, so you see, granted, I'm starting off with a very small, I'm starting off with a very small data set here. But again, start to put more items in here, have students play and make generalizations. You know what? Again, yes, this is the median right here, second quartile. But the thing is that students can just look at this and actually play with it and tell us a lot of things. Okay, really, really, really powerful. Okay, GeoGebra can make dot plots pretty well easily too. So let me just put some data in here: 6, 6, 6, 6, 6, 3, 3, 3, 2, 1, 2. Whoops. 2, 1, whatever, 2, kind of like that. And I can actually make a dot plot from L2. And see, I made a dot plot right there. Okay. And I change these values now. I can make the 6 of 5. I'll see changes pretty quickly there. All right. So again, it's you know, it's a work in progress here. But again, we're just looking at features and functions that this graphing calculator has that can help foster simple aha moments for students. Again, discovery learning and aha moments, light bulb off over the head, they do not need to be deep and elaborate and take days and days to build upon, and then boom, we have the grand finale, fireworks, right? They can be as simple and basic as this, but they just have to happen often. Just like in 2 weeks ago when we had part 1, we did a line of best fit, we got the correlation coefficient, and I asked you, as you know, people on the webinar, can you move the points to make the R value as high as possible? That's all I asked, and then everybody discovers, wow, the highest that the correlation ever gets is 1, right? The correlation coefficient gets is 1. The lowest it gets is -1. Students are discovering this through this app, and they are telling me, instead of, again, this is the antithesis of direct lecture. Why tell students if they can play and tell you? Because they can. All right, they totally can. So yeah. So again, feel free to throw some questions in, even in the YouTube chat as well. I know I have things I want to show you, but if you have questions about what I'm showing you, I'm definitely happy to you know, to answer them. I am trying to pay attention to it as best as I can here. But I'm going to refresh altogether, reload it. I want to show you something different. That's I thought was kind of cool here. Let's go to the graphing calculator, and right here down below is a freehand function. You got a pen? I love the freehand function because you could sketch graphs freehand, right? And people look at me like, really? It's like, yeah. Again, it's one of those tools that's hidden down below that like nobody knows exists until actually someone shows you. But it's like, see, with freehand function right there, sketch a function. Interesting. All right, so watch this. I'm actually going to kind of do a little curve here. I'll just keep it in the first quadrant, keep it simple. Ready? I'm holding my mouse down, and there. Done. Now, what are you going to do with it? Good question. I don't know. No, I'm just kidding. But right here, again, let me hide the grid lines here for a second. Get a little cleaner there. Again, I could take this and you know what I thought was really cool with this freehand function? If you click on it, right, it actually gives you what it thinks is relative extrema. I mean, isn't that insane? Right here and like right here. It's like, who does that? That's so cool. You know, and even still, let's actually draw one that crosses. It actually will give you roots and intercepts too. If you don't believe me, watch this. Here, you have at least one x-intercept, two x-intercepts, 3. Here's one, and I'll turn it off and look at this. It has a root at about -6.4, a relative extrema, given my shaky hand here, right? And then another root, the y-intercept. Oh, I almost made -1. See what I mean? Isn't that awesome? Yes, YouTube question. There is a document that lists all the commands. It's the Geogebra Manual somewhere. If you Google it, if you just if you Google Geogebra commands, it'll take you to the Geogebra. I forgot what it's called, like the Wikipedia wiki page, or like there's a Geogebra Manual. You look up any command, you'll find a whole list of commands, and in each you'll find 8 million of them, and you could click on any one, and it'll tell you all the ways you could type it and what it does, for sure. It's amazing. Yeah, the freehand function is amazing, Alfonso. I totally agree. But watch this. We're gonna play with this even more and get even crazier here. So let me delete this. Now I cannot move this function, right? I can't move this, but I wonder if it lets me. It does in the other apps, I think, but what if I did freehand of x minus 3? No, it doesn't do that because again, for check your input there, that will not work. But I know that in the classic app it does. But right here, I'm actually going to go plot a point on this object. Point on object. I'm going to plot 2 points actually here, and I'm going to put one over here. All right. Again, I got to turn that tool off by hitting the select arrow. Let me make it bigger here so I can see it better. Here. Now, if you are an elementary or middle school teacher, please don't leave. I just want to actually talk to pre-calc and calc teachers for a quick, maybe 5 minutes. But again, Algebra 1, there's still elements of this in here too. But I want to actually talk about the intermediate, I'm sorry, the mean value theorem. Okay, what does the mean value theorem say? Right, I mean, we need a function that is a continuous. Yes, this is, right? And let's actually draw a line here. Make line AB. All right. And so now, whoops, I'm going to keep A all the way down here and B all the way down here, up here. Okay. And I'm going to plot another point on here. GeoGebra calls it C. Okay, I'm going to style it. I'm going to make it red, actually. There we go. Right. So I like to ask students a lot when I talk calculus. I loved asking my students, hey, sketch me a freehand function. And they would do it in the class. Did it in the classic app, right? Sketch me a freehand function, and now I want you to draw the secant line connecting point A and point B, right? So they do, and so now what I would do with them, now keep it now. Well, before actually, students had more tools to use in the old graphing calculator in classic, but again, this graphing calculator has been stripped of its geometric construction features, right? So students have to think a little more critically now. I want you to move the C right here to a location that is guaranteed by the mean value theorem. So they got a little, what does it say? Oh, remember the mean value theorem. They got to dig back and say, oh yeah, mean value theorem says that if you have a continuous function, right? But from say from here x equals 1 to x equals looks like 14, right? Then there has to be an input value in the domain for which the derivative at that point is equal to the average rate of change from x equals a to x equals b, right? Or what we say the instantaneous rate of change, or geometrically speaking, the slope of the tangent line at C. So how do I make a tangent line at C? Well, students will look for the tangents tool, but oh, wait a minute, rats, the tangent function has been removed from this calculator in order to be compliant with high stakes exams. So gosh, how do we actually construct a tangent to C to this curve? What looks like a curve, right? You know what I mean? So again, we have to think critically here. Well, okay, first of all, don't we need the slope of this line? Again, the slope tool has been disabled. In fact, if I type in the slope of G, see here, G, oh. Now, if I did the same thing in the geometry app, it'd be a lot easier because it'd give me the slope triangle. It would make a tangent to that curve. It would do everything I wanted it to, right? But right here, or a line through, I'm kind of like, I got to somehow make this kind of from scratch. You know, think of this as almost like, you know, when you're making pancakes and waffles, you're doing it literally from scratch. You're not cheating and buying the process, the box, you know? So let's go back here and let's do this now. I got to find the slope of that secant line first, right? So isn't that really the fraction? That's the y coordinate of b minus the y coordinate of a all over the x coordinate of b minus the x coordinate of a, right? And just to be consistent, I'll even rename it as m, right? And so now, how do I write the equation? How do I write the equation of the line? This is a great Algebra 1 question for calculus students, because how many of you calc teachers know that it's never the calculus that's the problem? It's always the pre-calc, the modeling of the function, the building of the function, or even the skills they should remember from here, but they don't, right? So right here, right? So what would the equation of that line be? Y minus y of the y, let's just use point slope form, equals that slope times x minus x, the x coordinate of C, right there. That looks okay to me. I mean, I think that looks okay, but again, You see how the slope of that, those lines are parallel because we force them to be by typing the equation in like that. Okay, so right here, you look at it this way. This kind of looks like a good value. Maybe that, I don't know. But I want to show you another thing quickly here. It's almost half past, and we're going to get to the geometry app soon. But I want to show you something pretty cool here. Is that I'm actually going to first of all hide this. Again, if my students kind of show me this, I would say, yeah, that's awesome. I love it. But let's actually hide C, and let's actually hide the equation, and we're going to actually hide the line too. And what I'm going to do now is I'm going to put a lot of points on here, because what I'm going to do now is make a polynomial regression for these. And we'll see how close that regression comes to my sloppy handwriting here. But again, maybe I'm putting too many on here. I don't know. But again, I probably could have done a lot less. But let's just give it a shot and see what GeoGebra does. I'm kind of curious. Right there, and oh, Z is off. But whatever, we'll just keep it there. Okay. Now, I showed this in the first webinar, but I'm happy to show this again. And we're going to keep A and B there. But first, in order to do a polynomial of best fit, we need to actually create a list of all those points. And oh my gosh, it would take forever to do the open parentheses A, B, right? It's kind of like typing your L1, L2 on a TI. But instead, it's a lot easier here, because all you need to do is we'll get rid of everything but the points. And all you need to do now is go to your list tool, which is under the points menu right here. List. Whenever you want, here we have bivariate data, right? 2 coordinates. So I'm going to highlight a box around everything here. It says list L1 created. Okay. If you go back, there it is. See there? It's a quick way to put all the data in a list. And so now let's actually do the polynomial best fit. Let's do fit poly L1. Now, if I do that, GeoGebra chose a 21st degree polynomial for that, function I did. But again, notice all these coefficients are practically 0. So I think I could do, let's actually just see what let's just make a line. By the way, that's a line of best fit right there right now too. But you know what I'm going to do? I'm going to make a slider called K. And I'm going to make that slider go K equals 1. Let's let it go from 1 to say 10. Because I don't feel like, and we'll step it by ones. Again, K is going to represent the degree that we're going to make the polynomial of best fit, the best fit polynomial here. So I'll call this K instead. Yeah, line of best fit, we know, no good, right? 2, getting better, but still crappy. 3, wow, I think a cubic is doing pretty nicely, but watch what happens at 4, 5, 6. All right, 5, 6 does this. I mean, obviously it's got to be the same end behavior, both because of the even and the, but 7, that's pretty cool, right? 8 looks even better than that. I'm thinking, did I even get V on? No, I did put V on there. Okay, there we go. Yeah, but notice here, it's like it's kind of V is stuck to that thing there. Again, there's my my equation. It looks like it really 0, 0, but look, 0.001 x to the 6. So there it is. I can even show the value there in the label f of x, if you will. But now let's check this out. This is, students can you do this in calculus and say, well, we have all this. We can actually hide all those points, but we'll keep them up there for now to save time. But now let's go back and show the original freehand function. Let me actually make it bigger. Go to settings, style. See the freehand function I'm making thick, big, smaller. By the way, you can also go to the settings. You go to the 3 dots here. You can go, oh, wow, look at this, a freehand function, table of values. Let's make a table of values. Let's go from, say, 4 to 6. Going by, I didn't realize that. And I remember now, but wow. Let's go by, say, 1/5. Look at this. See, in my artificial freehand function that I drew, GeoGebra has the power to actually make me a table of values there. How cool is that? And I'm going to actually hide the list here. And I should get rid of all these points here. But if you look at that, that's pretty neat, right? And actually, let me just make I'm going to make the thickness of that, the thickness here. I'm going to literally make go to 0 so we can actually see better. I'm sorry, give me 1 second. Apologize. Style, go down. There you go, yeah. But you see here, I want you to also notice that when you make a table, see those black dots there? That's the sequence of points that we made in the table right here. Again, that's not on the blue graph. That is literally on the black freehand graph that I drew in the very beginning. Okay, pretty neat. So instead of giving students these contrived functions, let them just draw it by hand and analyze it that way. I think it is. Yes, John, I totally agree. It is amazingly cool. Absolutely. But let's get back to the original thing we were talking about here first. I want to find where I put my point C. There it is. And let's see. I think my best guesstimate was there. Sorry, it's getting messy here. I'm going to get my secant. I'm going to show my secant. Let me just delete the table. I want to get rid of, let me hide the points. What else did I want to do here? Also want to, I'm going to hide that polynomial function there for a second. H, there's my freehand. I made it so thin. Make it thicker again, right? But now let's show what I thought was a good spot for a tangent line. Well, right here. There was that, and there was the original line we did, right? But now, so how good was it? If we use the polynomial approximation to do that, wouldn't it really be the equivalent of finding h prime of, oh, by the way, there's the derivative of the function that I drew. I'm sorry, not that I drew. I'm sorry, not that I drew. I did, it's the polynomial, my bad. But if I did h prime of, what was it, x of c, sorry, h prime of x of c, it's about 0.682, and the slope of my line right here was roughly, where'd it go? Somewhere up here, 0.618. 618 thousandths versus 682 thousandths, not bad. Could I have done it better? Yeah, probably. Maybe I should have gone down a little bit. Was a little higher, right? Maybe here. I don't know. Point being, oh no, the slope is always 0.618. So the question is, where is this slope of roughly 0.618? And it's roughly, oh, that's pretty good, right? 613, 617. See the number changing there? But again, this is think of this as an alternate way we can actually have students explore the mean value theorem in calculus. It even slopes and even instantaneous rate of change in pre-calc, and there's anything like that. We can totally do this here within the graphing calculator. All right, but again, again, for high stakes exam bodies, governing bodies in the United States, this test meets all of the criteria that many of those restrictions that are imposed by those high stakes exam creators have. So again, if you're interested and you know someone's interested, you can email me, tim@geogebra.org, and with using this calculator for assessment, absolutely free to use for the purposes, again, of assessment. But again, let's go to the geometry app now. It's about 33 after the hour. Now, it looks very similar to the graphing calculator, but you'll notice it has a different feel automatically, right? There's no grid lines to start, and there's no place to type an equation. It just shows me tools first. And logically, that makes sense, because in geometry, don't you kind of want to start playing with the basic elements like this and then doing all that, right? Do whatever. But again, it's still, and notice how the descriptors are all qualitative now and not quantitative, right? This is an awesome app for elementary students. You want to make polygons, explore angles of triangles. This is the app to do it in. It really is. Let me delete all this. You can erase it like an easy teach board, like so. Okay. Now, let's see, what are we going to do here in the geometry app? Last webinar, we talked about a lot of geometric transformations, right? So let's actually, we did reflections, we did translations. Again, they're all in the first webinar here, but I want to talk about dilations to start off here. So let's just type in a slider, k = 1. That's going to serve as my scale factor. Okay. Now I'm going to go off here. I think I have it somewhere here. Nope. But I need to find a picture of something quickly. Give me a second. What cartoon character? Let's do Odie from Garfield. There he is. All right, get an image. We'll take that OD right there. Just drag him on my desktop, right in the corner. Nope, you didn't go. Sorry. Should have had him prepared ahead of time. There he is. Move him right there. And I love this. In any app, you could take it and you could bring it right in. Boom. There he is. Okay. Right there. And we can play with him. We can move him around. But you know what? Behind all this white space is a coordinate plane. We just need to show the axes and we just need to turn on the grid. Right? So there they are. So let's move A and B to convenient spots there, right? We can go to 5, 1. Maybe A can go to 1, 3. And I'll show the values here. And again, I love having my students get their own images, having them play, right? And just literally discovering many concepts for themselves. Students can tell you many. Again, I always challenge teachers to name me a theorem in geometry that you cannot have students discover in GeoGebra. There really is none in the standard geometry curriculum here. And it's all about how you scaffold. You know, some students need more scaffolding than others. So I will go in the geometry app ahead of time and maybe put a few things in so students can then build upon it. All right. Or I have students, I much prefer students come to a blank canvas right here and start building from scratch. That's way better, in my opinion. So right here, what we're going to do is we need another point now. Point. Plot it somewhere up here in the second quadrant. The reason why is if I plot a point right at 0, 0, it glues it. It thinks I'm talking about the intersection of both axes there. So C, we'll dilate about C since origin is a popular dilation center, right? We're going to dilate OD about C. But not only that, we're going to dilate this. I'm going to go to the segment tool right here. See right here. By the way, the segment tool is actually not in the graphing calculator. The reason why is because it's technically a geometric construction, right? Isn't that the most basic geometric construction, really? Because again, many exam governing bodies will not allow, because when you display the value of a segment, GeoGebra will output its length, but there are many high stakes test writers that don't want the length of a segment to be shown. They expect that students to be able to find that distance between 2 points algebraically, you know? Again, every country is different. Every state is different. I know in Europe, many exams in Europe assume that computer algebra systems already exist. So their tests are way different. The questions are, adjusted and asked in such a way that they know that that technology exists. But in many parts in America, it's not like that yet. But hey, it is what it is. And so that's why GeoGebra did what they did. So now, how do we dilate? We find the dilate tool, which you hit more. And again, this app is loaded. You can measure angles, construct angle bisectors, make perpendiculars, parallels, a lot of different things. But all we need is right here in this menu called transform. For now, we're going to do the dilate from point. Okay. Now to dilate in GeoGebra's, any one of GeoGebra's apps, all I need to do is, again, make a box around everything you want to dilate. I want to dilate OD and the 2 points in the segment. So I do that. Now I have to select the center dilation, which I'm gonna select C. And at this point, I now need to tell GeoGebra the scale factor. Sure, I could use a number, but remember at the very beginning, I made a slider called K. The reason why is because, and I have students make sliders all the time because I want them to play with them and see what happens dynamically to the image as I move that slider back and forth. So I hit OK. And then again, I need to turn that tool off by hitting the move arrow. And let's go to the calculator here. I can actually show it here or not, but we can bring this down. I ask, well, where's Odie? Where's the image? And the kids start playing with it. Oh, wow, he was on top of himself, right? Oh, by the way, you could take this image, and if you want to reduce the opacity, you could do the teardrop and make it a little bit faded so it's easier to see. But now you can ask your students the most basic of questions and have them tell you and discover quickly, when does an image of any object lie on top of itself? Well, when the scale factor is 1, right? When does the image disappear altogether? Well, when the scale factor is 0, that's really the center of dilation, right? And so now, talk to me about negative scale factors. What the heck does that do? And what if I just move this around? And what if, what if I didn't want to make C the center of my dilation center? You see what I mean? Yes, kids could do this on paper, but man, what I just did there in the last 10 seconds would probably take a half hour to 45 minutes to do on paper. But here, it's done so quickly and kids can explore, right? So what do we notice? And so basically kids start to realize and discover. So then I ask them to like show me the segments here. I say, okay, well, let's show the segment, the value and all that. And so here, I'll click on the segment, I'll give it the name, I'll show the label, the value, right? Wow, it's this is the same as that. The scale factor is -1. It looks like the length doesn't change, huh? Interesting. And so, oh, but now it's shorter. Now it's longer. But wait a minute. Let's just take Odie and make him just go for a second. Like really faded. Really faded. I tell kids, let's just look at the segments themselves. Forget Odie. Look at the segments F and F prime. What can you tell me about them? I'm talking this right here and this right here. Any observations? And students, you know what? I can move this around. They don't need, again, 90-something% of all students are able to tell me that, gosh, it looks like they're parallel. Well, Mr. B, are they always parallel? And what do? I don't say yes or no. No, I say, well, can you convince me they're parallel? Can you maybe use some of GeoGebra's tools to prove to me that they're parallel? Again, an informal proof, but can you convince me? You see, now we're actually, and there's a couple ways to do it too, right? Can anybody on the YouTube chat kind of give me some insight here? How can I convince myself that these segments are definitely parallel, no matter what the scale factor is? How can we prove it? Literally. Any ideas? I'll give you a hint. If you get the word more one more time, you'll see a couple tools that might be of interest here. But I think the magic one we need for one is right there, right? Remember, this tool is not in the graphing calculator because, again, students need to be able to find the slope of a line, right? If you're given 2 points, they should be able to find the slope. But here in the geometry app, you could just click on the segment there, and there's the slope. Yes, there it is. Right there. Well, Scott, diagonals bisecting each other, that would be, if the scale factor is -1 to make a parallelogram for sure, but I think for a trapezoid, I don't think that would be the case, but I could be wrong. No, actually, no, they wouldn't bisect each other. It looks like they wouldn't, but that was a good conjecture though. But yeah, here, see the slope tool right there? Gee, -2/5, -2/5. That's pretty cool. But what if so is that always the case? Yeah, it looks like it is, right? Or another way we could actually do it is we'll make a line through here in A. Why don't we actually take the time to measure a pair of corresponding angles, perhaps, with the angle tool? Aha! So there, and then, okay, so C, A, B, C, A prime, B prime. Okay. So to answer that last question, how to use many dilations in one slider, typically you want to use one dilation per slider. I find that otherwise I'd find it be way too confusing for students personally. But yeah, but right here, you see you have what you have. Wow, there's more proof that those segments are indeed parallel. And look at how clear the image looks too. It's like Odie and his big tongue, right? I mean, we'll make the scale factor 5. You can see it going out to Kingdom Come here, right? Pretty cool. What you can do with GeoGebra's geometry app right here. But I'm going to refresh the page. We're going to start with a blank geometry slate again, but this time I'm going to take a more of like an engineering problem, like where do I put stores here? But just to save time, where'd it go? It's geometry. Nope. Hang on a second. Should be ready here. Where'd it go? Nope. Where is it? There it is. Wrong folder. There it is. Home Depot, right? I always like to have kids. I talk with kids about students. I might have showed this in another webinar. I don't remember, but about whenever you see a store like a McDonald's, what do you always see right down the street? A Burger King, right? Okay, what about a seat for those of you watching in the United States, maybe a CVS pharmacy? What's their biggest competitor? And if you're in the United States, you probably say, well, Walgreens, right? Walgreens and CVS want to each put a dent in each other's business, right? So, and Home Depot, the orange, and then you have the competitor, which is Lowe's, right? So again, right here I have a map of, and from my home state of Connecticut. I grew up in a town called Southington right here, and right here where you see these mile markers, these markers, these are locations of Home Depots, right? In my old hometown, there are 2 Home Depots actually. So take that orange, make that orange here. Oh, all right. And so now Home Depot, the store Home Depot was built first. Lowe's came about maybe 5 to 10, whatever years later. So those stores were built reactively, right? And so, you know, they're going to want to put a dent in their business. So if you have a town called Sellington now, and all of a sudden, you know, they're going to they put up a Lowe's there probably in 2000, maybe a little bit. Where do you think that they're going to want to put it? Right now, if you're from Connecticut, you might know where it is, but if you're a student out in Nebraska or California, you have no clue of Connecticut's mainland, whatever, might be a great problem for you could engage students with. Go to store locator, right? Home Depot store locators, find some Home Depot locations in a state that you don't live in, all right? And then do the same for Lowe's. And then you can type addresses in here. I'll show you another website that I often had kids go to. It's called mapcustomizer.com. Again, it's called mapcustomizer.com. All right. And so you can actually plot addresses. Statue of Liberty, Empire State Building, right? How about Battery Park? Some popular New York touristy spots. I'm going to take a screenshot of that now. There it is. And I can throw that screenshot in the GeoGebra in the GeoGebra Geometry app and start trying to figure out, gosh, where should I put my restaurant if I want to be kind of like equally accessible to everybody? You know, contrast an activity like that to assess students versus like giving them 8 problems. Point P is on the perpendicular bisector of segment AB. PA equals 2x plus 4, PB. You get what I'm saying, right? Yes, students should be able to do those problems, of course, but you know, let's make it kind of, you know, more real world. Now, granted, this is a very simplistic way of approaching a problem like this because we also have to consider factors like population density, transit, all that stuff, way more complicated. But again, we're relating it to some simple geometry concepts students are using here. Okay, so now I want to take this here and go back here for a second. And basically, yes, whether I use the compass tool or literally just have students create the perpendicular bisector, which is right here, right? Any point on that perpendicular bisector is going to be equidistant from those 2 endpoints. And we could use GeoGebra to validate that, but I'm not going to just to save time. I'm going to put a point there, right? And yeah, EC and ED are definitely equal, but let me show you something I found really cool. I'm going to delete that altogether, and I'm going to go back in that same folder I had, and I'm going to show you that same picture now with the Lowe's plotted in there. So here it is. Remember, the Lowe's is in blue, right? That marker is where the competitor store is. So right here, I got to find, there's D. Let me bring this back. So point C is right here. Point D is right over here. Check it out. Not bad. And interestingly enough here, there's one over here in Berlin, Connecticut, the town in which I used to teach, and over here in Middletown. And right smack dab, literally, it's almost the midpoint, not quite, but literally the one in Cromwell lies on the perpendicular bisector. It's kind of cool. I actually plotted a bunch of the same stores, and it's almost like they make like this kind of a circle around this very heavily populated area. It's pretty cool. But again, it's all about discovery learning, and in this case, yeah, maybe discovery, but at the same time, a simple application of a concept that often students are kind of like, I don't feel like solving for X anymore. You know, just something to think about. Maybe something like this could serve as a performance-based assessment. That's like a 15-point quiz where students can work in groups of 2 or 3. and then they hand them the final product. I love giving quizzes to like 2 or 3 students, but everybody does their part of the work, you know. But yeah. So anyway, let's keep going here. Let's actually talk about. I want to talk about locus for a couple minutes here. GeoGebra has a locus tool. All right, that's again. I want to focus in the second part on a lot of the tools that are not often seen and used right here. So I'm going to go to more again. There's a tool down here called locus. You know, locus being a set of points that satisfy like a certain condition right there. Okay. But one activity that I love to do it first by paper folding with patty paper. Again, yes, I love GeoGebra very much, but at the same time, I never ruled out the hands-on paper folding and, you know, compass, you know, like hands-on. Students still need to be engaged with that. I always loved having a combination of the digital and the hands-on. But again, both methods still constitute student-centered active learning and not passive learning with a lecture where I want to fall asleep. Okay, so right here, I like to have I've had students make a circle on paper. So you're going to see the digital analog of what you can have students do on paper at least. And we're going to actually construct line AB here. Actually, no. Yeah. So line AB, maybe no. Hang on a second. Yeah. So first, give me a second. We're going to put a point in the circle right here. Okay. And we're going to actually now put a point on the circle. Again, B is just the radius changer. That's all that's going to do. It's going to make it bigger or smaller. But I want a point that I want to move around the circle. So point on object right there. I have students put, you know, this point right here, literally, will just kind of move around the circle. Okay. Going to make the perpendicular bisector now. Again, students build first, they reason later. All right. In this particular activity, perpendicular bisector, right? We'll make the perpendicular bisector of CD. Okay. And now, okay, what we're going to do is actually we're going to construct. I'm going to construct line AB. So that's what I did. Oh no, line AD for a second. There we go. Right. And again, remember D can move around the circle here. And I'm actually going to plot use the intersect tool right here, or you can use the point tool. That'll work just as well. The intersect tool will tell me where those lines intersect right there. Turn it off. I'm actually going to make this point. I'm going to change the color. I'll make it a nice pinky color here and kind of go make the thickness a little bigger there. That point E. Right? Now watch this. Now with E, you can actually turn the trace of that point on. So if I right click on E, I can show as D moves around the circle, I can show where E is going. Now right click on D, let's animate it and see what happens. Feel free to type in the chat. What do you get? What is that locus of points? That all the possible locations for point E in the plane here. What does it make? Let's try this again. Maybe I should, hang on a second. Maybe I should go here and let me make E a little bit smaller. It's probably a little too thick. That's better. Yeah. Let's move C here. By the way, if you want to make a trace disappear, just zoom in and zoom out really quick. That's a quick trick. All right, and then we'll move D around here. You got it, Scott. Yes, Alfonso, it's definitely an ellipse. But I always ask students now. I mean, yes, I have held the thumbtacks on the board with the rope in between, and we show, hey guys, the distance between the two is constant, right? The constant length between. Yes, many of us have done that. But how is that illustrated here? Let me actually move this pointer around again. Animate it. And A and C are actually foci of that ellipse. No matter what I do, they'll always be foci. Let's do it. See here. We can make another ellipse to zoom in, zoom out. There we go, another ellipse. Move the foci together. Don't you get a circle? Just about, right? But why is it an ellipse? And that's the why. The logic is actually very simple here. I'll show you why here. And again, and if you try this on patty paper, just plot a bazillion points here on the circle and just fold C to all those points on the circle, those crease lines form the perpendicular bisector. And that locus of the envelope folding, like what do they call it? Envelope, the curves. But actually, I can even do this. I can actually right click on the line and show the trace here. And watch this. Let's play D one more time. You can see it there. Pretty cool. Move the point E outside the circle. What do you think you get? Inside, C. Let me zoom out here. If you actually move C outside the circle, let's watch what happens now. What is that locus called? It's definitely a hyperbola. Yep. I can shut the things off there. But here's why. Let me, this is getting messy and ugly here. Logic is simply this, okay? Notice here, remember here, hang on a second. I got to turn that trace off because I'm going to get a big headache if I don't. I'll show that trace there. There we go. E, I'm gonna turn E off, the trace E off as well. So here's the logic, right? The radius of a circle is always constant, is it not? Right? So if you look at the logic here, right? AE plus ED is a constant. I'm going to actually write that down for a second. AE plus ED equals radius equals constant. Right? That'll never change. But if you look here, if E is on the perpendicular bisector of segment CD, doesn't that also mean that what? There's text there. That also means that ED is equal to EC, does it not? Because of that. So AE plus ED is a radius. That's a constant. But wait a minute. This is equal to that. And so if all I do is substitute this in, EC and for ED, that's why AE plus EC, that's a constant. That's what makes the ellipse. I'll show it again really quickly, show the trace. And let's play this point. Whoop. I got to turn the tool off, my bad. Let me animate this one more time. So AE plus EC is now a constant right there. If that makes sense there. You got it. Absolutely, Scott. Indeed. And now, and for the logic there, it's the subtraction. When you move C outside, you have basically, what's the logic here? That now it's the same logic, but just going in a subtraction sense here. See how right here, CE and ED are constant, but so now DE minus DA is a constant. You see the logic there? DE subtract DA, that leaves you the radius. And since now CE and DE are equal, that's why you substitute in, you get the difference being a constant there. All right, it's pretty cool. One last thing I wanted to show you here. I know we have like 2 or 3 minutes. I might go 2 or 3 over. I apologize. You know, I went under a little before, but I do have to show you this really quickly, which I thought was so cool. I mean, I've seen it before and I've played with it before, but I've never really shown it in a webinar or a live demonstration. I know Steve Phelps has done a lot with this, but right here, there is a reflect about circle. I mean, we all talk about the typical transformations in geometry, right? But what the heck does it mean? How do you reflect something about a circle? That's interesting, isn't it? So I guess we must need a circle first. So let's go ahead and make one. And let's play and reflect. So there's a circle. And let me just make a point here. I'll put a point in the circle here. So now I'm going to reflect C about the circle. Huh, interesting. Okay, so C is the image. C is the pre-image. C is the image. But gosh, it looks like any point that lies on the circle, students discover, automatically gets mapped onto itself. That, I guess that sort of makes sense, you know. But what? Whoa! The closer C gets to the circle, the closer its image gets. But they discover that when the pre-image gets closer to the center, it's like the image wants to like take off out to infinity. Like, what's going on here, right? And so that's where students it starts getting very, very intriguing here of what it actually means. Now, I know I'm running out of time. I thought I'd have more time to show you this, but turns out it's almost like the basically the product of this and the product of this distance and that distance is actually equal to the square of the radius of the circle. But I think I said that correctly. Yeah. But basically, they're very related, like, like almost like in a reciprocality kind of thing, But what happens when you reflect a triangle about a circle? Again, let me just make a quick polygon here. I'll even make a. I'll just make a, what is that, a hexagon or 1, 2, 3, 4, 5 pentagon. If I reflect this about a circle, check this out. Lasso all that. Look at that. What the heck is that thing, right? But see how the image of E gets on there? Okay. Now students can start, you can have your students start having a field day with this, right? And they can even research online, do stuff. It's pretty amazing what you can do with reflecting in circle. And if I move this in the circle, holy moly, look at that. You have all sorts of pretty cool, crazy contraptions going on right there. And so I zoom out, right? Again, the sky's the limit to what you can do with these apps. Again, if you want to know what any one of these commands do, just click on it, like whatever, just click on it and then go to the help right there. You'll take you right to the how to use it right there. So yeah, but I want to respect the time. Thank you so much for joining me in this deep dive part 2. A lot of exciting things coming to GeoGebra. A couple of releases to the website and a new app coming out in the next several months. So stay tuned for that. Next Wednesday night at 9:00 p.m. Steve Phelps will be facilitating the webinar using GeoGebra 3D to teach calculus. Many of you AP calculus teachers watching, or calculus teachers, the AP exam's over almost, and it's like, what do we do for the rest of the year? Now we're distance learning at home. Steve Phelps has a lot of great, awesome ideas for you coming next week, 9:00 p.m. on Wednesday, May the 13th. Wednesday, May 13th, 9:00 p.m., GeoGebra's YouTube channel. The YouTube link will not be created until about 15 minutes before the start of it, but just go to GeoGebra's videos page. You'll see it pop up once he goes live. So thanks again for watching. If you have any questions about anything, feel free to email me, tim@geogebra.org. Happy to help. And I wish you and your students the very best for the rest of this academic year. And so, yeah, thank you for watching. Have a good night.